There's a few more things that we actually need in order to complete this example, because it tells you how to do a forward pass through your model. If I give you the weights and the biases, then you can actually do a forward pass. You should be able to implement this in NumPy, a forward pass. Okay, you won't ever do that, but you should be able to. Okay, what you would definitely never do is, the actual question is, how do you train this model? How do you actually figure out what the weights and biases are? Okay, you will probably never in your life implement that in NumPy, except if you really like pain and suffering, but you might do that in PyTorch. Yeah, PyTorch or TensorFlow or JAX. So what do we need to figure out what those weights and biases are? I told you that neural networks are basically two things. Multiplying stuff together, like inputs with matrices, okay? And then there's maybe it's more than two things, maybe it's like three things, okay? And then what else do you need for neural network land? A loss function that you are going to push down in order to get the right values for your matrices and your vectors. Okay, so we need a loss function. Okay, so hold on to your seat here. Let me very, very quickly just say, like, spoil the whole story for you. But basically your loss function is going to be a loss function composed of basically however long your training sequence is. You're going to sum up a whole bunch of little loss functions at each position. And what, for instance, the first loss function is going to measure is how good is this vector in predicting the word a? How good is this vector in predicting the word long? How good is this vector in predicting the word time? And you're going to sum up all of those little loss functions. Does that make sense? So an RNN language model outputs a vector yt at every time step, and there should be a hat there. Okay? And how you can think about this is that, remember, it's a whole vector, right? So y hat t is this vector with values between 0 and 1, and they sum to 1. Okay, so you've got a whole vector here. That's your y hat. And how you can think about this is that the kth element in that vector, right, if this is position k, that little value here, that gives me the probability of the next word belonging to the class k. Does that make sense? Based on everything that happened up to that time step. Okay. So this is really what the model outputs. It gives me a prediction of the probability of the next word given everything I've seen up to this point. Okay, cool. And what we can do now is we can think of each of the outputs of the model as having its own little loss function yt. Okay? So we've got a y1, a y2, a y3, and then we're going to sum all of that up. Okay. J of theta, what is it? Okay, we're going to use the negative log likelihood, which is what we've been using the whole time. So the negative log likelihood in this case is I'm going to sum up all the log likelihoods over my sequence length for the log of the probability predicted by my model for observing this particular word at time step t plus 1, given everything that happened before it. Okay, so that's just the log likelihood of the sequence that I've observed. Okay, I jumble my notation a little bit here because sometimes I use like xt plus 1 to refer to the particular word occurring at that place, and sometimes I think of it as a one-odd vector. So sometimes I think of xt plus 1 as a one-odd vector with a 1 in the position for the word that occurs at that specific position, right? But you guys are clever enough to, from the context, figure out that, you know, sometimes it's the actual word and sometimes it's a one-odd vector representing that word. Okay, that's just to explain my sloppy notation. Okay, so we've got this xt plus 1. Okay, and we've got the probability of xt plus 1 given everything that I've observed before. Now, what our model outputs is a vector at time step t, and this vector has values. Sorry, this is a one-odd vector, so there would be zeros and there would be a 1 at some position. This prediction from my model yt, that's a whole bunch of numbers, maybe a 0.1, a 0.001, and so on. Okay, and up with some number in that blue position there. Okay, and what I want here is I want to write down the number in the blue position. Okay, and mathematically, one way to do that is to basically sum up over this vector and just keep the element that corresponds to that blue point. Okay, so mathematically how you can do that, I know this is quite rigorous, but it's good because you might have to implement this by hand at some point, or at least test a model. So what you're going to do is you're going to start at little k equal to 1, which is this top position, and then you're going to run down up to v, which is the vocabulary size. And then what you're going to check is xt plus 1, this vector here, is it on or off at position k? Okay. Then I'm going to multiply that with the log of the corresponding item in my predicted vector, ytk. Okay. So this, just stare at that a second, but it's a very fancy way of saying I pick the item in my vector corresponding to the word that's in my training data at that specific position. So you could have written that a little bit more concisely, maybe something like this, where you just say, I'm just taking the log of the predicted probability at time step t, which of the elements in my vector, whatever occurs at t plus 1. And now this thing, what I'm going to do is I'm just going to call this gt of theta, where gt theta is equal to the negative log of y hat t, okay, at the element x plus 1. So this is just a very fancy way of splitting up my loss function so that I can look at things at every particular time step. Okay. I need to mention this just in case you're going to implement this in PyTorch. The function that you actually use for this loss function will be called the cross entropy loss. Why? Because you can actually, and you can go and show this by looking up the definition of cross entropy loss on Wikipedia, but the cross entropy between the vector xt plus 1 and the vector ht, if xt plus 1 is this one-odd vector, so the cross entropy between this vector and this vector turns out to be exactly this thing, if xt plus 1 is a one-odd vector, which it is in this case. So in PyTorch, you would probably use the cross entropy loss function class in order to implement this thing. Okay, excellent. So let's just look at our model again. At time step 0, you have a vector that comes out here. You look at the element within that vector corresponding to the word a, and you take the negative of the log of that. That gives you your first little loss term. At the second time step, you feed in the word okay? You get an output here. That output is based on what happened in this hidden state here. And then you look at the element in that vector corresponding to the word long, and you take negative log of that and you write that down there. And you do that for every one of your little time steps, and that is then your overall loss if you sum it up. In practice, what you would do is you would normally normalize by the number of little loss functions as well. So very often you have a 1 over, and I've got a t plus 1 here because I explicitly add a start symbol. If you don't have a start symbol, then it will just be 1 over t that you put in there, okay, which means there you have a 1 over t plus 1. And that's just to scale the loss function so that regardless of your data set size, you get similarly scaled numbers that you would put in there. Okay.